Hello everyone, welcome to the first video in the MAE 2360 online only lecture series. The second half of this class is all about proposing problems commonly found in engineering, finding some clever way to let the computer do the math for you. So, since this is the first video, we're going to start off with something simple. Today we're going to be talking about roots finding algorithms. For our first algorithm, let's look at something simple. Let's start with some function f of x, and we're going to set it equal to 0. Now, what could f of x be? It could be something simple. It could be 3x plus 2. It could be something more complicated. It could be a polynomial, 3x squared plus 2, or it could be trigonometric, 3 cosine 2x, etc. Now, when I say that f of x is equal to 0, there's a couple of words for this. You might think solution. For example, if we take this one right here, we set this one equal to 0, clearly we can solve for the value of x, right? We can move the 2 to the other side, we can divide. That gives us the solution to this function right here. There's another word for it. When the function is specifically set equal to 0 and then solving for the unknowns, this is also called the root of the function. So what we're going to be looking at are some algorithms to help us find the roots of the functions. Let's also talk about what the roots of the function are graphically. So we have some claim here, f of x is equal to 0. This is where the roots are. If we were to plot this function, here on the x-axis we have our independent. Our independent here is x, so here is x. And then we are plotting some value here of f of x. So f of x, it could be some kind of function. Here's the function. There we go. So up here on top, we're saying that f of x is equal to 0. Okay, well, here's f of x on the vertical, and here is the value 0. So here on the chart, where is f of x equal to 0? Well, it's equal to 0 right here, and it's equal to 0 right here, it's equal to 0 here, equal to 0 here, and maybe it's equal to 0 at some other points in the future or some points here in the past. We don't know, it's just that over this interval we have 1, 2, 3, 4 roots. These locations right here, where f of x is equal to 0, these would be the roots. So when I say these are the roots, what we're literally saying is that here at this point, x equals some value. We can call this one x1. Here we can say that x equals x2. Here would be x equals x3. There's x equals x4. Those would be the 4 roots of this function f of x. So what we want to do is we want to find some algorithm we can put in the computer that's going to help us find these points. First method we're going to talk about is the bisection method. This comes from the mean value theorem. Now, what this theorem says is if you have some function f of x, so given a function f of x that is continuous over an interval, let's say x1 to x2. So you have some function f of x and we're defining it over some interval x1 to x2. If f prime of x exists for the whole interval, and if f of x1 times f of x2 is less than 0, then if all of these are true, then there is at least one root of f of x on this interval. x1 to x2. Okay, so let's talk about this. What does this mean? We have some function, and remember, we're looking for the roots of this function, right? The bisection method is going to be a roots finding algorithm. If we can prove these things, if we can say that it's continuous over an interval, if we can say that it's differentiable on that interval, and if you solve this, you solve the function at 2 points, right? F of x1 and f of x2. We're saying that if you multiply these two together and they're less than -1, consider what that means. That means f at some number is positive and f at some other number is negative, right? If this is less than 0, then this thing has to be negative, which means these two numbers right here have to be different signs. One has to be positive, one has to be negative. The implication then is that somewhere in between x1 and x2, it crossed the 0, right? It crossed the x-axis. If it crossed the x-axis, then it did a sign change. And this right here is really testing for a sign change over that interval. Let's look at it graphically. Here's the function. It can be doing something like this. There we go. What we're going to do is we're going to specify an interval. We, the user, we're going to provide an x1 and an x2. And remember what the conditions are. The function, here it is, needs to be continuous over that interval, which means you can't have any discontinuities. It needs to be differentiable, which means it needs to be, again, smooth with no discontinuities. And you need to have a sign change, right? We're going to evaluate f of x at 2 points. We're going to multiply those together. They need to be negative. Consider what happens if we selected 2 points down here. Let's say we select x1 and x2. Now, we have some knowledge of the behavior of f of x. We have a plot of it. We have some kind of data, so we can look at it and say, yes, okay, this is continuous, and it does have a derivative. If we were to evaluate the function f at these 2 points, what are we talking about? Well, it's literally the value of the function, right? Here are the values x1 and x2. So we could say that this is f1, and here is f2. If we look at this, clearly f1 and f2 are both positive, right? So if I take f1 and I multiply by f2, then this is not less than 0, right? This is two positive numbers multiplied together. And it doesn't matter the magnitude of them, right? This could be like 1 over 10, and this could be 1 over 100. It doesn't matter. They're both positive. Similarly, what would happen if we chose different ones? What if we picked an x3 right here and an x4 right here? So here would be, here is f3, here is f4. We can just see graphically both of these are negative. So if we do f3 multiplied by f4, well, negative times the negative is going to make it positive, right? So again, this is not less than 0. What we would like to do is we would like to pick some kind of interval where there is a sign change. So let's do this again, one more time. This time, let's pick the interval x1 to x2 where there is a sign change. Let's say that we pick x1 right here and x2 right here. Now, graphically, we can look at this thing. We can see that there is some kind of sign change, right? Here would be f1. Here would be f2. If we were to take f1 and multiply by f2, well, f1 is negative and f2 is positive, right? So again, it doesn't matter the magnitudes of these numbers. The only thing that matters is with one negative and one positive, you end up with a sign change. And this value right here, when you multiply them together, this value is going to be negative. Now, remember the goal of this is to find the root, right? So what is the root on this? It's this number right here. It's the value of x, right? That makes f of x equal 0. Similarly, there's also a root here. So either of these two, right, these would be acceptable roots. Now, for the interval we selected x1 to x2, and there's only one root in between. What if we had selected x1 over here? Well, if we go from x1 to x2, these are both positive, right? So this evaluation, even though we can look at this and we can see that there are roots here, this evaluation does not hold, okay? So you need to pick some kind of numbers such that this is true. So we've selected this x1 and this x2. Let's talk about what this bisection method is going to do. Let's take this and let's zoom in on the interval that we've selected. What we're going to do with the bisection method is we're going to take this interval x1 to x2 and we're going to bisect it. So really we're just going to cut it in half. Let's take the value that is the average of x1 and x2, the midpoint between them, and let's plot it. So that's going to be about right here. Let's call that x3. So we've taken this, this interval, we checked that f of x1 and f of x2, there's a sign change here. So we know that there's some root in between. We're going to split it right in the middle. So here's x3. Now we're going to ask a question. We're going to try to determine where the root is. Is the root in the first half or is the root in the second half? Well, clearly, I mean, there it is, right? There's the root. So what we can do is we can treat this x1 to x3. We can say, okay, here is one interval, and then x3 to x2. We can say, okay, here's another interval. So on this first interval is the root there. On the second interval is the root there. Clearly, it can't be in both, right? So how can we check to figure out if the root is here? Well, we're going to use the mean value theorem, the same thing we put forward just a minute ago. Only now, if this is f1, and this one here is f3, and here is f2, what we're going to check now is we're going to check if there's a sign change between f1 and f3. So if I say f1 multiplied by f3, is this less than 0? Well, if it is less than 0, it means one of these is negative and the other one is positive, right? So that means there's a sign change. And if there's a sign change on the interval, then there's a root in that interval. And from the picture, we can clearly see f1 is going to be some negative number and f3 is going to be positive. So this would evaluate as true, right? And when it does evaluate as true, that tells the programmer that the root is in the first section. So what would have happened if we had selected x3 just slightly different? What if we had picked, it came out such that x3 was actually right here. I can call this like x3 prime, right? If it just so happened. Well, that means that the root would not be in this interval, and then f3 prime right here. If you take f1 and f3 prime and you multiply them together, you get a positive number, right? Because they're both negative. In which case, that means the root is simply in the other half of the interval. So, what's going to happen next? Well, we perform this original check with 0.3, and it comes back, and this comes back as true, right? That tells us that it's in this interval. So, what we would do next is we would say, okay, let's ignore the whole rest of this, and now we're just going to focus on this part of the interval. So, now we're just looking at something like this. So we had our original x1 was right here. Let's say x1 and f1. And then we had this new point over here at the end of the interval. This one was, it was x3, right? So here was f3. So now we just have some new interval to look at, and we want to find the root. Well, where's the root? Right there. How can we do it? Well, we just need to keep doing this, the mean value theorem, over and over and over again. So now on this new pass, it's x1 and x3. Let's make this one number 2. So this now is x2, f2. This is the new x2. So what are we going to do? We're going to bisect it. Okay. We're going to come about halfway. Here's about halfway. And we're going to call this one x3. We're going to call this f3. What do we do next? Next, we check for a sign change. I say f1 multiplied by f3. I ask the question, is this less than 0? And in this case, well, f1 is negative, f3 is negative. You multiply them together, you get a positive, so this is not true. What this evaluating is not true, what does that tell us? What does that tell the computer? It tells the computer the root is not here, the root is over here. So, what do we do next? Well, we ignore now this part of the interval, and then we redraw the figure. There we go, something like this. So this time now, there was x2, this was x3, here was f3. Okay, we want to find the root. Where is it? Here it is. What are we going to do? We're going to bisect the interval. Okay, this time let the 3's become the new 1's. There you go. Bisect the interval. Here is x3. Here is f3. So, what's going to happen? Again, you applied this, this criteria right here. You check for a sign change. And I think at this point you can probably see what's going to happen. We're going to cut it in half. It's going to be on this interval. We can see that. We're going to take this interval and we're going to cut it in half. And then it's going to be here in this space. We're going to take this and going to cut it in half. And eventually, maybe, we're going to keep zooming in on it closer and closer and closer until all of this space right here, you can imagine this space having its own plot, right? And then you keep zooming in, and zooming in. So, we can see that this is going to zoom in on the root. We have an issue, though, of when do we stop? When is it good enough? Now's a good time to talk about numerical tolerances. We're going to be doing math problems in the computer, right? Let's say that the actual answer is 14. So the answer to some problem you're working, x equals 14. And because you're solving this in a computer, it doesn't find 14 exactly. It comes back and it finds, let's say, 14.326. Okay, that's pretty good. You let your bisection method run another round. This time it comes back and the answer is 13.971. Well, it overshot the target, right? We were above 14, now we're below 14, but this one is closer to the actual value 14 than the one before it, right? So you let the algorithm run one more time. This time it comes back and it says, okay, the answer is 14.006. Okay, that's getting better. You let it run another time. Now it's 13.9991. You do it again, 14.000003, etc., etc. You see what's happening. Every time your algorithm runs, maybe you bounce back and forth across the target, above the target, below the target, but you get a little bit closer, right? A little bit closer to this actual answer, and that's ultimately what we want. Now, in many cases, the computer is never actually going to find the real answer. You're never going to get 14.0. So what we need to do is we need to define some kind of tolerance. Usually, you see this in literature, you see this in books. This is usually done with the Greek letter epsilon. Epsilon usually just means some small number. You, the user, specify epsilon, okay? So let's say that here is some value that we're coming up with. We're calling it x1. And let's say that the actual answer, x, is here. So what we would say is we would say take x1 minus x, and let's take the absolute value of this. We're not concerned whether we're a little bit above or a little bit below, at least not in this problem. So take the difference between them, take the absolute value, and if this number right here is less than epsilon, then what we're going to do is we're going to force our algorithms to stop. We're going to say that our answer has converged to the true answer, and then we're going to call it. Now, in this example, this one required us to know what the actual answer was, right? And if you know what the actual answer is, then what are we doing here to begin with? What if we did this? We may know that the answer is 14, okay? The computer doesn't necessarily know that the answer is 14. So let's say that we're using this bisection method and we're bouncing between values, and we get some bounds, some new interval, x1 to x2, okay? So here's the new interval, and we know that some root exists on this interval, right? Because we can check. We can do an evaluation on this, a sign check. We can see that there's some kind of root. So what we'll do now is we'll just modify this, and we'll say x1 minus x2. So remember the x1 and x2, these are the two bounds on your interval, right? And these are going to get closer and closer together. They're basically going to box in the actual correct answer from both sides. So we want this to get very small. We're effectively looking at the window here. How big is this interval? So you take the absolute value of the difference between them. If it's less than some number that you specify, 10 to the negative fifth, 10 to the negative 10th, right? If this is true, then stop. Okay, having talked about all the theory on the bisection method, let's talk next about the pseudocode for it. So if you're not familiar with that word, pseudocode, think of it as a recipe. It's just a step-by-step instructions of what needs to happen inside of your computer code to solve the particular problem. So let's come up with the pseudocode for the bisection method. Step number 1. Choose x1 and x2 such that f of x1 multiplied by f of x2 less than or equal to 0. So there's our original condition on the interval having a sign change in it. Number 2, set x3 equal to x1 plus x2 divided by 2. So again, this is the bisection, right? We're saying that x3 is equal to the midpoint between x1 and x2. Number 3, we're going to ask the question, if f of x1 multiplied by f of x3 is less than 0. Remember, this is a condition for a sign change, right? We're saying if the sign change is on the first interval, then we're going to set x2 equal to x3. Understand what this step is doing. x2 is the upper bound of your active interval. So we are resizing the interval now to be from x1 to x3. What happens if this fails though? Else. Now, if this fails, that means that the root is not on that first interval. It means it's in the second. So the second interval needs to go from this x3 up to x2. So what we're going to do is we're going to overwrite x1. Otherwise, you set x1 equal to x3, and this moves you up to the second half of the interval. And then 5, now we just repeat steps, let's see, 2 through 4 until, okay. So we're going to do this over and over and over again, right? We're just going to repeat steps 2, 3, 4, 2, 3, 4. Find the midpoint, evaluate the interval, resize the interval. When do we stop? Well, we're going to stop when we hit our convergence threshold. So every time you do a new round, right? So every time you hit number 4 and you go back to do number 2, we're going to perform an evaluation. We're going to take the current values of x1 and x2. We're going to find the absolute value of the difference between them. And as soon as that dips below a threshold, and there's an or what happens if f of x is exactly equal to 0? There's always the possibility that you either get lucky or you have a good initial guess and you can nail that original convergence. Sometimes that happens. But we're going to repeat these steps really until this convergent threshold is reached. Once this is reached, some small number here, 10 to the negative fifth, 10 to the negative 10th, something, again, you set it. Once this is reached, then you stop and you simply print the current value of x. There is a third condition. We're going to say, or, what if, let's say your current iteration is greater than some maximum iteration. What does this mean? You're probably going to need to run this logic in some kind of loop, right? You want to let this process repeat over and over and over again until this has happened, until you have converged. Now, this is a numerical process. Sometimes if you write this algorithm, this will actually never happen. Sometimes your algorithm is not going to converge. And there's all kinds of reasons that can happen. We'll see several examples of that happening with the Newton-Raphson method. What you want to do is you want to specify some maximum number of cycles. This is in a while loop, this is running 5 times, 10 times, 100 times. Maybe you want to set it to 100, 200, 1,000 times. And just tell it, hey, if you reach 1,000 iterations and you have not yet converged, go ahead and call it and then print your final results. Okay, everyone, that's it for the first video in the series, the bisection method. Next time, we'll come back and we'll talk about the Newton-Raphson approach.